Hello friends, in this lecture we will discuss one more form of grammar which is a linear grammar. I will tell you what linear grammar is and what are the different types of linear grammar, and then we will see the different topics related to linear grammar. Now, first of all, what is linear grammar? So linear grammar is one form of regular grammar. So as you know friend, regular grammar is fourth kind of grammar in Chomsky hierarchy. In Chomsky hierarchy, and all the productions of this grammar is of the form A gives A B and A gives small a. So these two kind of productions are possible in regular grammar. And if your grammar is generating epsilon, then only one productions you can have with epsilon in regular grammar. So as I told you, linear grammar is one form of regular grammar. So linear grammar again you can represent in the same way. So now linear grammar is nothing but a regular grammar. And as you can write the production of regular grammar, so in the same way you can write production of linear grammar also. So there are two types of production in linear grammar. First is left linear grammar, where you can have productions like A gives B A and A gives A, like this. So now this is left linear grammar. This is left linear grammar, where in the right hand side only one variable will be there, which will be at leftmost position. And in linear grammar, you can have more than one terminal, but all terminals must be in consecutive string, as a consecutive string. Like you can also have A gives B A, like this. And the second type of linear grammar is right linear grammar. It is right linear grammar. And in this particular type, you will have production like A gives A B or A gives A. So here in right linear grammar, the variable in right hand side will have rightmost position. Rightmost position. Now, again, like this, you can have more than one terminal in the right hand side. So all these terminals must be in as a consecutive string, like AAB. AAB. So now this is how you can write the production of left linear grammar and right linear grammar. Now I will tell you very important and interesting thing about left linear grammar and right linear grammar. So now suppose I take one example grammar here, as gives A S and BS and A. As gives AS, BS and A. This is right linear grammar. This is right linear grammar. As you can see, the production are of this type. Now, the language of this grammar is A plus B whole positive clean closure and A. That means it will generate, this particular grammar will generate all strings of A and B ending with A. Ending with A. Now suppose I convert this particular this right linear grammar into left linear grammar just by reversing the right hand side of production, then it will be like this. S gives SA, SB and A. So now I have converted this grammar into from right linear to left linear grammar just by reversing the right hand side of each production. Now, what would be the language of this particular grammar? That is interesting. The language of this grammar would be A followed by clean closure of A plus B. Clean closure of A plus B. Now you can notice, friend, the language of right linear grammar was A plus B whole clean closure followed by A. the all strings of A and B ending with A. Now, if I convert this right linear grammar into left linear grammar just by reversing the right hand side of each production, then the language generated by this grammar will also be reversed, or you can say the reverse of the original language. So it was generating all strings of A and B ending with A. Now this particular grammar will generate all strings of A and B starting with A. So this is very interesting and very useful thing about left linear grammar and right linear grammar, and this property we will use in some conversion. So I hope this would be very much clear. So if I convert any left linear grammar into right linear, or any right linear grammar into left linear grammar, then the language generated by the grammar will also be reversed. So this is a very important thing. Now, as I told you, linear grammar is one form of regular grammar, and regular grammar generates regular languages. So language generated by all linear grammar would always be regular, and if it is a regular language, then definitely we can create regular expression for this, and we can create finite automata for this. That finite automata may be NFA, maybe NFA with epsilon move, maybe DFA. So any finite automata we can create for linear grammar. So now next we will discuss how to convert any particular linear grammar into finite automata. So I hope till now the process is very clear. So I will take now one example grammar, and we will convert that particular grammar into finite automata. So now friend, we will discuss linear conversion of linear grammar into finite automata. Now one important thing, as I told you, there are two types of linear grammar, right linear grammar and left linear grammar. So for right linear grammar, we can directly convert into finite automata. So how we can convert any production into transition? See, in grammar, we have production rules, and in finite automata, we have transitions from one state to another. So whenever we are getting some production, so we need to convert that particular production into corresponding transition rule. So how to perform this conversion, that we will discuss now. So now friends, we will take this grammar as example, and we will convert this particular grammar into finite automata. Now as you can see friend, here there is only one variable. There is only one variable, and there are two terminals A and B. So these two terminals of grammar will become the input symbols of finite automata, and all the variables of the grammar becomes states of the finite automata. So now we can say the minimum number of states in the finite automata will be the number of variables in the grammar. So as we have one variable in this grammar, as we have one variable in this grammar, so at least one state would be there in finite automata. There may be more states also, but at least the number of states in finite automata will be the number of variables in the grammar. So now I will tell you how to convert any particular production rule into transition. So now suppose you have A gives small a B, this transition this production rule you have. So now you can consider this left hand side variable as current state of machine, current state of finite automata. So you can create two states here, so A and B. Now if this is your current state, that particular and that is the input symbol you are reading, and this is your next state. So you can convert this particular production into transition like this. like this. So I hope it is clear. Now, another kind of production is A gives small a. A gives small a. So now, if your production is having only one terminal in the right hand side, then you can create one transition of that particular terminal from that particular state to final state. You can directly make a transition to final state from this state. So there is no final state now. So I can have one more state here, which you can consider as final state. So I can create one transition of A directly to this. Now, suppose your grammar is generating epsilon. So in that case also, you will have one production as A gives epsilon. So in that case, whatever variable is generating epsilon, the state corresponding to that variable you can consider as final state. So here, as A is generating epsilon, so you can create A as final state. So this is how you can convert all types of productions into transitions. Now I will take this grammar as example and we will convert this grammar into finite automata. So now we will convert any given RLG to FA. Now this is RLG, right linear grammar. So we will convert this right linear grammar into finite automata. So now, as you can see, there is only one variable. So we can create at least one state here, and whatever star symbol is your in your grammar is, you can create, you can make corresponding state as initial state. So as it is having only one variable, so I can create this state and make it initial state. Now on A, we have production as gives AS. So this is your current state and this is your next state on this particular transition. So you can create one self loop of A to on S. Then again we have S gives BS. So you can create one more self loop of B on S. Then you have S gives A. So as I told you, in case your production is having only one terminal at right hand side, so you can directly create one transition of that particular terminal to final state. So I can create one more state here which you can consider as final state, and I can create one transition of this from S. So this is the equivalent finite automata which is accepting language generated by this grammar. So I hope this is very much clear. Now we will see another conversion, LLG to FA, left linear grammar to FA. So now friends, this is one left linear grammar and we will now convert this particular left linear grammar into finite automata. So now as you can see friend, we can directly convert right linear grammar into finite automata by converting each production into corresponding transition. Now, in order to convert any left linear grammar to finite automata, we will use this method. See, first we will convert this particular grammar into right linear grammar just by reversing the right hand side of each production. So in order to so now I will tell you the steps of converting any left linear grammar into finite automata. So first step is convert given LLG to RLG by reversing right hand side of each production. Now convert reversed LLG into finite automata. Then third step, as I told you earlier, like when you are converting left linear grammar into right linear grammar just by reversing the right hand side of each production, so whatever language that LLG is generating, the right linear grammar will generate the reverse of that language. Now when you are converting any LLG to RLG, So suppose this is generating this LLG is generating language L. Now if you convert this LLG into RLG, so the language generated by this RLG would be reversal of L, reversal of L. Now, when you convert this RLG to finite automata, so this finite automata will also generate reversal, will also accept a string of reversal of L. This finite automata will also accept strings of reversal of L, strings in reversal of L. Now, if I want to create finite automata for accepting language L, then we can convert initial state into final state and final state into initial state, and we can reverse all the direction of transitions. So we have seen this particular property while we discussed about closure property of regular languages. So for any particular language, if language is regular language, then reversal of this language is also regular, and finite automata for reversal of language you can create as by converting the initial state into final state and final state into initial state and reversing all the directions of transitions. So then you we can write third step as reverse the direction of each transition in finite automata and interchange initial and final states. Now, I will tell you the same process in one more form. Suppose you are required to convert any LLG to FA. Convert any LLG to FA. So that means what if the language of L is the language of LLG is L, then this finite automata must also accept L. Now, if we are in first step, as we are converting LLG to RLG, so LLG to RLG, so the language of this LLG is L, and we are converting it to RLG. So the language of this RLG would be reversal of L. Now, we will convert this RLG into finite automata. So, we will convert this RLG into finite automata. So, language accepted by this finite automata will also be reversal of L. And then in third step, we reverse all the directions of each transition, reverse the directions of each transition in finite automata and interchange the initial state and final state, so that converted finite automata, I am representing it as FA dash, will accept the reverse language. So now you can see you have converted LLG into FA. So this is how you can convert LLG into FA. So this is the process of converting any left linear grammar into finite automata. I hope it would be very much clear. Now we will uh, consider this grammar as example. We will consider this grammar as example, and we will create one finite automata for this. So now suppose this is our given grammar, which is LLG, So we will now convert it into RLG just by reversing the right hand side. So I can write it as AA, BB, A. Then A gives AB, B, and B gives BA, A, like this. Now, whatever the language of this grammar is, the reversal of that language would be generated by this grammar. Now, we will create finite automata for this. So as there are three variables, that means at least three states would be there. So I can create three states, 1, 2, and 3, like this. Now, as S is our start variable, so we will make this state as initial state. Now we have transitions as gives a small a, capital A. So we can convert this particular transition into, sorry, we can convert this particular production into transition like this. Then we have another transition, sorry, another production as gives small b and capital B. So I can create like this B. Now we have as gives A. So there is only one terminal in the right hand side. So that means this transition must be going to final state. So I can create one more state here, final state, and now I can create one transition of A from this S. Now on A, if we are applying small a, we are moving to B. So I can create one transition like this, A. Then A gives A gives B only. So I can create one transition to final state directly, B. Now on B, if we are applying a small b, we are moving to A. So I can create one transition like this. And on B, if we are applying A, so we are moving to final state. So this is the finite automata for this particular grammar. Now, the, the language of this grammar is L. The language of this grammar is reversal L. And as this finite automata is for this grammar, so the language accepted by this particular finite automata will also be reversal of L. Now we need to create finite automata to accept L. So now how we would be creating? So we can now convert initial state into final state and final state into initial state and reverse all the direction of and reverse the directions of all transitions. So I can create equivalent machine here, S, then A, then B, then I can create one final state, F, one more state like this. Now we have to convert this into initial state. So I can make it initial state, and we have to make initial state as final state. So I have to make this also. Now from S, if we are applying a small a, so we are moving to A. So now we can reverse its direction. Then we can reverse its direction also. Then we can reverse its direction also. Then we can reverse its direction also. Then we can reverse this direction also. And A. And so this is now the machine, the finite automata that will, if the language of this finite automata is reversal of L, then the language accepted by this finite automata would be L. So now you can see this is the given grammar in LLG form, left linear form, and this is the finite automata corresponding to this left linear grammar. So this is how you can convert any LLG into finite automata. Any LLG into finite automata. So I hope the process is very much clear to all of you. And if you have some doubt, you can always write to me in comments. Now I will discuss one more conversion of one language RLG to LLG and LLG to RLG, and the process is exactly same. So one example I will take, remaining example you can do it yourself. So now friends, we will see the conversion of one LLG into RLG and RLG into LLG. So suppose we are converting RLG into LLG. Now conversion means if the RLG generating the language L, then this LLG must also generate L. So now how we will be doing this particular conversion? The all conversions we have discussed. So now you can convert it yourself. Like first convert this RLG into FA, and then FA to reverse FA. Then this FA to reverse FA to RLD. So you can see this particular, if the language of this RLG is L, then converting this would be converted into L, and then the reverse conversion, reverse of this particular would be LR. Then you convert it into equivalent RLG. You convert it into equivalent RLG. So this RLG will also generate LR. And then by reversing the transition of this particular RLG, you can convert it into LLG. And if the language of this RLG is reversal of L, then the language of this LLG would be L. So you can see you have converted RLG, which is generating language L, to LLG, which is also generating the same language L. So I hope it is very much clear.